Let's start by looking at some integrals you probably have seen in Calc 1. The first one I want to look at is the integral of 1 over 1 plus x squared dx. The quickest way of doing this integral is to remember that it's the derivative of inverse tangent. So the derivative of inverse tangent of x is 1 over 1 plus x squared. Therefore, the integral of 1 over 1 plus x squared dx is inverse tangent of x plus c. So likewise, we have other related integrals that can be dealt with the same way, like the integral of 1 over square root of 1 minus x squared dx is just going to be inverse sine of x plus c. And another one that you probably have seen is the integral of 1 over absolute value of x times square root of x squared minus 1 dx. This is inverse secant of x plus c. Now, there are some integrals that are quite interesting or that are quite involved to deal with that we don't have a method for so far. Integrals like, so I'm going to say, how about integrals like okay, integral of 1 over square root of x squared plus 1 dx. I mean, we have 1 over square root of 1 minus x squared dx, and we know that it's the inverse sine of x plus c. But we don't have any quick way of getting this. Okay, how about something like the integral of square root of x squared minus 4 dx? Okay, we have 1 minus x squared. We have something like this, but this is going to be difficult. If we use u substitution, let's say we start by saying let u be x squared minus 4. If you take the derivative, you get 2x. There is no x outside. There's no x somewhere here to cancel out with the 2x. So that makes it difficult. And maybe something like, how about when we have something like this? The integral of, say, 16 minus x squared cubed dx, etc. Things like that. Okay. So these integrals are challenging, but there is something about them. The one thing about them is that they have x squared in it. They involve x squared. So all these involve x squared, something like this involving x squared. So the fact that they involve x squared could give us some motivation to think of how we can make use of the integrals, the three integrals I listed above, Now, that motivation boils down to a bunch of rules that I'm just going to state, and I won't explain it, and then when I do an example, I'll tell you how to use those rules and explain it, and explain them during that time. All right, so don't worry too much about understanding what these rules are. So the rules, I'm going to try to make a table. It's usually hard to make a table here. Let's see, make a table. Okay. Okay. I'm gonna write the heading down, rules, and then I'm gonna put a table. Okay. So try to draw a line. No, that line is too far. So these are the things that make my videos long. You may want to like fast forward until I finish drawing this line. That might help. Okay. All right. So what's this rule about? So I'm gonna have a column that says if integral contains, so if integral the integral contains, oh no, so if the integral contains, if it contains, say, ax if it contains a squared minus x squared, where a is a constant, what kind of trig substitution do I use? What kind of substitution do I use? And I'm going to, I won't explain what trig substitution is. When we do an example, you'll see what it is. So the kind of trig substitution I'll use will be x is equal to a sine theta. All right. And a useful identity is, identity to remember, trig identity to remember would be something like sine squared theta plus cosine squared theta is equal to 1. All right. Now, if the integral contains a squared plus x squared, then you have to make the trig substitution x is equal to a tangent of theta, and you think of the identity 1 plus tangent squared theta is equal to secant squared theta. All right. Now, if the integral contains x squared minus a squared, then you have to make the substitution x is equal to a secant of theta, and you use the trig identity 1 plus. You might not need to use it, but it's just useful to remember. Okay, now why am I writing all this? Let's see. The first integral here, this one, this contains x squared plus 1, which you can write as x squared plus 1 squared. And we use the second rule over here, a squared plus x squared, or x squared plus a squared, and so forth. Then the second integral, square root of x minus 4, you can think of it as x squared minus 2 squared, or x squared minus a squared. And this is the kind of trig substitution we use. So this is where the name comes from, because it's a trig substitution. You're substituting a trig function for x. Now, let's do one of these examples. How about we start with this integral right here, this one. integral 1 over square root of x squared plus 1. If it were just 1 over 1 plus x squared dx, then we know what to do, but now it involves square root. All right. Examples. No, this is thicker now. I don't want it. He is too thick. All right. All right. So the first one about the integral of 1 over the square root. Oh no. Square root of I think x squared plus 1. Dx. Now, this has, if you think of think about it as x squared plus a squared, or a squared plus x squared, where your a in this case is 1. So I'm going to rewrite it for us to clearly see how it fits into one of our categories. So this becomes, we can write it as the integral of 1 over square root of 1 squared plus x squared dx. So our a clearly is 1. So let's do our trig substitution by the side here. So if we let's do it in green. All right, so we have a squared plus x squared. So we're going to use a tangent of theta as x. So we're going to say let x be equal to a, our a is 1, tangent of theta. All right. Now, as you know, in every substitution, we start by taking the derivative. dA, dx, d theta, in this case, is secant squared of theta. This implies that dx is equal to secant squared d theta. All right, now, so we go back to our integral. We have 1 over, in place of x squared is now tangent squared theta. All right, and dx is now secant squared theta d theta. So we've changed everything from x to theta. Everything has to be in terms of theta before you take your derivative, or you take your integral, sorry. So this is the integral of 1. If you remember the trig identity that we studied, and the one that I have listed over here, I've listed some trig identity. I said one important one is that 1 plus tangent squared theta is secant squared theta. So this is just going to be, the denominator now is going to be square root of secant squared theta. And then you have secant squared theta d theta. So this becomes integral. The square root of secant squared theta is secant of theta. So you have secant theta times secant squared theta d theta. So if you simplify, you just end up with secant theta, d theta. Okay. So this will give you natural log. Go back to the video, the part 2 of trig integrals. We solved the integral of secant of theta, and it's just the natural log of secant of theta plus tangent of theta plus c. But this doesn't look complete. This is not complete because our original problem was in terms of x. Now we have it in terms of theta. So we need to return to x. And how do we return to x? We have to go back to our initial substitution. We said let x be equal to 1 plus tangent of theta, right here, over here. Let x be 1 plus tangent of theta. So we can use that to figure out what secant of theta is and what tangent of theta is. We already know what tangent of theta is x. What is secant of theta? Now let me show you how to do this. What you have to do is you draw a triangle, right angle triangle, right? You're using the fact that, oh no, what is happening? Using the fact that, let me make it a little bigger. I don't know. Can I make it bigger? Come on. All right. Usually big just means crappy, but no. I told you, big means crappy. Okay. So you have x is 1 tangent theta. So that means that tangent theta, you can say that tangent of theta is equal to x over 1. So if tangent of theta is x over 1, if theta is here, tangent is opposite over adjacent. So this is x over 1. If you use Pythagoras theorem, you can find this side. This is the hypotenuse. So the hypotenuse is the square root of the opposite plus the adjacent. So it's x squared plus 1. With this, you can find any trig ratio you want to find for this triangle. So that means we can find what our secant is, secant of theta. Secant of theta is 1 over the cosine of theta. So secant of theta over here, secant of theta becomes hypotenuse x squared plus 1 over adjacent. So we just go in here. Our answer becomes, final answer, natural log secant of theta square root of x squared plus 1 tangent of theta x plus c. So that's our integral, and that's how you use trig substitution. So I'm hoping this table makes sense, is making more sense now, because we've made use of number 2. Maybe let me label them. 1, Roman numeral 1, Roman numeral 2, and 3. So we've made use of rule 2 now. Okay, now let's look at a second example. Let's see. Okay. Let's try Which one should I try? I'm conflicted. Very, very, very conflicted. Okay, so let's try number 2, square root of 4 minus x squared integral dx. Okay, so we can begin by making a substitution. We just have to realize that this is the same thing as the square root of 2 squared minus x squared dx. Okay, so this is the same thing as 2 squared. It's like a squared. Think about it. It's like a squared minus x squared. A is a constant, all right? So think of 2 squared minus x squared. So we're going to use the substitution x is equal to 2 sine theta. So let's go ahead and try that. Let x equals 2 sine theta. If that's the case, dx d theta is equal to 2 cosine theta, so that we get that dx is equal to 2 cosine theta d theta. So now our goal is to change everything to theta. So we end up with the integral square root of 2 squared minus x squared becomes 4 sine squared theta. So I'm going to change this to 4, what it originally was. But then our dx is 2 cosine theta d theta. Okay, so what do we have? We have this integral. The square root, we can deal with it in a kind of way. We can factor out a 4, factor out the square root of 4, or let's factor out a 4 inside the square root. We're left with 1 minus sine squared theta, which is something familiar, and then we have 2 cosine theta d theta. All right, so if you factor out the square root of 4, it just becomes 2. So we factor out a 2 here. Actually, we can factor out both 2's. We can factor out, why am I saying 2? Because this is a 2. If you factor out this square root of 4, it becomes a 2, and we can factor out also this 2. So let's factor out, if you multiply both of them, you get 4. Factor out a 4, and then we are left with a square root of 1 minus sine squared theta times cosine theta d theta. Okay, so this is 4, and then we have square root of 1 minus sine squared theta. We can think of it as square root of cosine squared theta times cosine theta d theta. But the square root of cosine squared theta is just cosine theta. So this is actually 4 integral cosine squared theta d theta. All right. If you remember when we did trig integral, we say that when we have an odd power, we can factor out something. But when we have an even power, and that's the only thing we have, then we have to use the double angle formula. So in this case, we have 4, and then our integral cosine squared theta can be written as 1/2. times 1 plus cosine of 2 theta d theta. All right. So this gives us, if you multiply the 4 and the 1/2, you get 2. Integral 1 plus cosine of 2 theta d theta. Okay. So in that case, you get 2 times theta plus or minus, plus actually, the integral of cosine 2 theta is 1 over 2 sine of 2 theta d theta. All right. Now, our substitution is in terms of x, and it gives us sine of theta. We don't have any sine of 2 theta, so we're ending up with sine of 2 theta. But think about this. If you think back to pre-calc, you'll realize that sine of 2 theta can be written as, so this is 1/2. Sine of 2 theta can be written as 2 sine of theta cosine of theta. And why did I put the theta here? This should be plus c. Sorry about that. Plus c. So we have everything in terms of theta now, not in terms of 2 theta, but we need to go back to x. So I'm going to copy this. I'm going to copy this. And I'll bring it right here so we can see where we are. Change it to red. Oh no. All right. So our goal is to go back from theta to x. So if x is equal to 2 sine theta, this means that sine theta, so this means that sine theta is equal to x over 2. So let's draw our triangle and see how that informs the dimension, the size of our triangle. So if we draw our triangle like this, this is theta, then this is opposite, and this is hypotenuse. Okay? So we need cosine of theta. So we need to use Pythagoras theorem, which tells us that the adjacent is going to be hypotenuse squared, 2 squared, minus opposite squared. So we have the sides of the triangle complete, and we can find any trig ratio we want to find now. Okay? So this means that we can say, so cosine of theta is adjacent square root of 4 minus x squared over hypotenuse 2. Okay, so we go in here, and also we need to look for theta. Sorry about that, but theta now is quite easy. We need theta and we need cosine theta. So let's do it this way. So x is 2 sine theta. That means that sine theta is equal to x over 2, and also we can say also theta is equal to inverse sine of x over 2. Okay, so look at what am I doing? I wanted an expression for theta, and I also wanted an expression for cosine theta because I need them to express my answer in terms of x. All right, theta and cosine theta. So if I go now to my answer, theta is inverse sine of x over 2, right? And then this 1/2 and 2 just multiply each other and they go out. All right, so the sine theta is x over 2, so plus x over 2, and then cosine theta is square root of 4 minus x squared over 2. All right, so we can have maybe multiply through, you get 2. No need to multiply through, just put the 2 outside here. Plus x square root of 4 minus x squared over 4 plus c. So that's our final answer. We're Gucci. All right, so what else can we do? Can we do more stuff? Let's try one more. I don't want to get carried away. Okay, I want you to try some, but I'm not so sure of my answer. So why make you try them when I'm not so sure of my answer? All right, so I want to okay, so let's try this one. I'm gonna start it off and I'm gonna let it be. So this is the integral of square root of 9x squared minus 25 all over x cubed dx. Now, this is not quite easy to see, or maybe you see it already. Sometimes I don't see something and then I feel like everybody doesn't see it. I'm sure you've seen it. So we can write this as 3x all squared. 9x can be written as 3x squared. Then minus 5 squared over x cubed dx. Okay. So let's go back to our trig identities or our rules. All right. If you have x squared minus a squared, all right, then in this case we have 3x squared minus a squared. Okay, so instead of making x equals a secant of theta, what you can do is say 3x is equal to a secant of theta. So that's what we're going to do here. We're going to say let 3x be equal to 5 secant of theta. All right, and then we can say that means x is 5 over 3 secant of theta, and then the x d theta is equal to 5 over 3 secant theta tangent theta and dx, 5/3 secant theta, tangent theta, d theta. I'm already tired of writing. All right, so let's see. Plug everything in. 3x squared becomes 3x is 5 secant of theta. 3x squared becomes 25 secant squared minus 5 squared is 25. So we have that, and then we have x cubed, which is 5 over x is 5/3 secant of theta. So this becomes it becomes 125 over 27. That is ugly. I don't like what I'm seeing. Secant cube theta. And then our dx becomes 5/3 secant theta, tangent theta, d theta. So if that's the case, we can go ahead and the numerator, we can factor out a square root of 25, and then we're left with the square root of secant squared theta minus 1. And then let's rewrite this as 5/3 cube. Why not? So that we can cancel things a little bit more neatly. We can cancel this and cancel one of those, and cancel one of those, and it just becomes 2. We can cancel secant and cancel one of those. It just becomes 2 also. And then let's see what we have so far. We have square root of 25, which is 5. And then at the denominator, we have 5/3 squared secant squared theta. And then we have tangent theta d theta. So this becomes, we can factor out the 5, and we can factor out the 5 squared over 3. So let's do all that. So factor out the 25 and 5 squared over 3. So that becomes, let's just keep it here like this. So you factor out the square root of 25, that's just 5. And then you have factor of 5 squared over 3. That leaves you with 5 squared. And then you bring the 3 at the top. And then this cancel one of this. I'm thinking we have 3/5, but I might be wrong. No, 3 squared over 5. 9/5. Okay, well, let me just do it by the side. What the hell? So you have 5/25/9. Bring the 9 to the top. They have 5/25. So you just have 9/5. That's what we have. All right. Okay, so outside, we're going to factor out a 9/5. And then the inside, we still have square root of secant squared theta minus 1 over secant squared theta times tangent theta d theta. Okay, I don't know how this is working out so far, but something is making me uncomfortable, but we're gonna be fine, I think. All right, the square root. I think The square root of secant squared theta minus 1 is the square root of tangent squared theta. So it's just tangent squared. It's just, the top is just tangent theta. And we multiply by one of the other tangent thetas, which is, I'm just going to rewrite. And then we have secant squared theta. Now, something is happening that, so we end up with 9 over 5 integral tangent squared theta all over secant squared theta d theta. Okay, let's make sure we didn't make any mistake somewhere. Well, let's stop here. I'm not going to tell you the answer. My advice for you is to look for any mistake along the way, and then we'll figure out the answer in class. Okay? All right, let's stop here. Bye.